Yeah, thank you. I'm Martin Stein, and I'm working in Genode Labs in Bristol for about like 6 years now. And today I want to talk about user level networking in Genode, to say everything that you can do between the microkernel and your web applications. So in general, Genode is like a building block system. So you have a lot of building blocks, and you put them together to your individual solution. And so there are some building blocks that are for networking, and I will give an overview today. The first chapter will be a big picture about all the components, and then we will orient on them in this picture through the other chapters. The first is about the drivers that we have, and then about the controlling tools, so say tools that are used as interception tools for the networking session that we have on top of the drivers. And then we speak a little bit about what front ends exist and how this is implemented. And at the end, I will give a little motivation for applications and look on applications that already exist. So, first to the overview. I have separated them, as said, in 4 layers. You have these drivers. We have the main drivers that now exist, and they support. They use the device I/O that is supported by that is provided by the core of Genode, and all give a generic interface, the NIC session interface. And with this NIC session interface, you can do all the controlling stuff. So you can do routing, you can do encryption, and other things that you want to do bump in a wire between 2 NIC sessions. And then on top of that, you have this front end layer where you adapt to your application what your application needs. So let's start. I will also go a little bit into the history of the components. First, the wired NIC driver. In Genode, we had at the first place a port of Linux, of the Linux NIC driver, especially for the PC net cards of OMD in the year of 2009. But this was merely for the QEMU compatibility, and later it realized that we need some support for actual hardware that is built into laptops that we use. So the laptops that we used had almost all these 1000 series of Intel built in, so we needed some more support. And at this point, it was a good option to go to the GPXE project to look at this code. GPXE is like a network bootloader project that is the successor of FOSDEM, and it is a pretty small, slim framework. It is easy to port, and so we switched to this and had then support for the Intel network cards. In the year 2011, we discovered that the GPXE sources were a little bit inactive, so there was not much activity by the developers, and so there was the official successor of the GPXE project, the IPXE, and we took an approach to this and switched to these newer sources. So we are more up to date, and support for new cards can be enabled easily. Okay. There's also and USB as a NIC support over USB. You can use, this is ported from the Linux sources. We use it especially for these ports here, the Exynos 5 SOC, Comet 4 SOC, and Broadcom SOCs, because we used things like the Thunderbolt or the Arndale board, and Broadcom is the Raspberry Pi. So there you need network over USB. Okay. We go on with the Wi-Fi driver. The Wi-Fi driver was initially a port of the Met Wi-Fi, port of Linux, and it enabled us the FRS chipsets, that especially these ones that are listed here. And yeah, over the years, it came in place that we wanted more these Intel Wi-Fi cards to have supported, and this was enabled with the port of IVL Wi-Fi, and we took this as opportunity to port also the whole Wi-Fi stack of Linux. And the VPA certificate, because with the Met Wi-Fi we had no protection, for instance. So yeah, only unprotected Wi-Fi. And yeah, this was quite some work. I think it took about 6 months or so to get this monster of a code base ported and regulated. And yeah, what came out is this Wi-Fi driver component that works as follows. I will give a short overview. The Wi-Fi driver component takes the IQ PCI session to talk with the device, of course, and then you have some ROM module that you get in, and this ROM module contains, at the beginning, it contains the WLAN that you want to connect to, or it contains nothing. It can be empty too. So the Wi-Fi driver then scans, of course, the WLANs that are available, and it provides to you a report. This is like a file, but it's not really the same. But it gives you in this report a list of all available Wi-Fis, so you can connect, you can choose from these ones and this ones, and it also gives you information about signal quality, protection types, and so on. And if you have not configured yet this Wi-Fi inside the VLAN configuration, you can now put it in, and it tries to connect. So this VLAN configuration, the Wi-Fi driver always, all the time listens to this VLAN configuration. And all the time it changes, it tries to reconnect to the Wi-Fi you configured in here. And the end product of that is the report VLAN state. In this VLAN state you can see if you are connected and to which Wi-Fi you're connected. And yeah, I can hopefully, yeah, I can show this here, of course. In my scenario, this is an local runtime link where we have these access points. There are the access points listed, all the values. And the state shows that we are successfully connected with FOSDEM VLAN to a state. Okay. And here we also have the DSS. Okay. Okay, the next thing is pretty simple. It's Nick Lubeck. I have not much to explain about this. It took a NIC session from it provides a NIC session where you can put something in, and it's not highly sophisticated. Okay, we go into the controlling tools. Maybe the first thing that was in the queue was the NIC bridge. The NIC bridge implements some flavor of the proxy ARP protocol, and it monitors the ARP, and the DHCP that goes on the NIC sessions, and tries to get some mapping about the clients that are connected to this. And that is, it is like an OSI layer 3 switch. So what you have is it has one uplink at the downside, at the bottom, and multiple clients that can connect at the other side, and you can either leave it to the NIC bridge to collect this information, these relations between IP addresses and MAC addresses, or you can also configure it statically. So you can say this NIC line 1 has IP address so and so, and line 2 has IP address so and so, and the MAC addresses are allocated for each line. So it creates some virtual MAC addresses for each line. Okay, and then it forwards packets that can come from the uplink or from our clients according to their destination IP addresses. That's all. Okay. Now for the NIC router. The NIC router is a little bit. It started with a pretty small set of features that we wanted to achieve, and especially we wanted to have NAT, and it ended up in implementing a whole level 3, layer 3, layer 4 routing component that now knows routing for IPv4, TCP, and UDP. It can also do NAT, of course, for TCP and UDP. And we have port forwarding for these two layer 4 protocols. And yeah, in the past we had also the problem that we wanted to do DHCP. We wanted to have DHCP for the single domains behind the NIC router. And originally the plan was to do DHCP outside of the NIC router and to do an extra component, and then we would reconfigure the NIC router. But for the first step, we thought it was nice to have this DHCP inside the NIC router because it's not much code actually. But yeah, in the future this will maybe get outside the NIC router to an extra component. But there we would have to do an extra component that manages the reconfiguration of the NIC router. Yeah. Then the NIC router can also show you a quite big log of all the packets that go through them and all the decisions it makes. So you can have a really good insight into what's going on in your virtual networks and who is communicating with whom. But of course, this is also a little bit bloated. Not all the time you want to see all the packets. But it's cool for debugging. And also it can record statistics to the outer world. So it provides a report file. In this report file you have such things like how many packets go through one domain, how many were sent, how many were received, and so on and so on. How many fails there are. And yeah. And this is a short overview over the functionality of the NIC router. So you have several domains. Each domain is like a set of rules. to each domain there are these rules and the DHCP role connected. So in general, you could say that the domain is like a virtual network, a virtual subnet. And to each domain, there can connect multiple NIC sessions. And the uplink of the NIC router is not special in this. It's also only a domain. And what we have here, the only difference what we have here is that by now, the uplink is the only domain that creates a session. That is the server for a session, the client for a session, for a NIC session. It creates normally a NIC session to the driver or to whatever we get our network or physical subnet. Yeah, so far. Okay, I can show a short example for this. Because in the scenario I'm using, there's also a NIC router, and it manages to manages the different applications that I have now running. And you can see here, this is the configuration of the NIC router. We have several domains, uplink, Evox, and socket as Evox Firefox, and so on. And there are several rules, like here we have for TCP or UDP, where we permit any port, in this case, to go to uplink, or we want to filter out for a specific subnetwork, to reroute to socket address, and so on. And we have here the DHCP server configuration of one domain. So we have the DNS server, IPs, and so on. Yeah. And you can also see here, I will use the pencil pointer, that you can either go with a static configuration of the NIC router's IP config for the domain, or you can tell the NIC router to get its own configuration over DHCP. So it will play at the uplink DHCP client and get its own configuration this way. Yeah. Mm-hmm. Okay. Now the NIC dump. This is a simple component that is bump in the wire, a real bump in the wire component for, we put it in between two NIC sessions, and it shows us all the traffic that goes through. So it logs, it puts out a log for all the packet headers of these protocols that are listed here by now. And yeah, you can configure the detail of the log, and you can also switch on timestamps. Okay, Tor. Yeah, Tor, I think everyone knows Tor. It's a project that aims for anonymized TCP connections over so-called onion routing. So it uses several Tor nodes in the network to reroute a connection into anonymized it. And we had a board, I think 2 years ago or so, of the version, it was an earlier version first, like 0 to 4 or so. And we are not so far away from the latest version, but this is currently merely experimental. We don't test it that much. It works, as far as I can tell. I have tested it yesterday, and it comes up. It can connect to the network and get a drink together. But there's one demo scenario you can try. It's the Eigencore run in the Word repository. And this would try to do fetch over URL over the Tor. So what we do in here is essentially we take the NIC router again, and we have behind one domain the fetch URL, and behind the other domain there is the Tor. And we configure the fetch URL domain in such a way that it can only connect to the Tor domain and to the Tor port, the 9050 port. And so all the traffic of the fetch URL must go over the Tor, and the Tor then has access to all to the internet over the uplink. So you can ensure that you won't go unsecured with applications that you don't trust. Okay, next, OpenVPN. With OpenVPN, you can tunnel to virtual private networks, and this goes again bump in wire, so you have one NIC session at the one side, and one NIC session at the other side, and it works transparently. So yeah, I don't think I have to explain this much. We have ported version 2.3.4, and this is 2.4.4. I don't know, there's some progress in work, but it's still experimental. So we don't test it that much, but I know that there are guys that work with this, and it's not abandoned in this way. But you have only the bridging mode right now, so you can only do Ethernet. Okay. The front-end tools. First I will go into the stakes that we have and how they evolve. This is the IP stakes. Initially, the initial stack we had for TCP/IP was the lightweight IP stack. It was ported as lib, so you can link it against each component individually. And it is accompanied by a libc plugin. So we have in Genode this concept of the libc that is like empty in the initial state, and you put some plugins behind it that fulfill your needs, your requirements. And the lightweight IP stack libc plugin is such a plugin that you can put behind your libc, and then you have the lightweight IP as functionality of libc. So this way you won't have to incorporate the whole libc in every component just because you need one functionality of libc. In 2013, we started experimenting a little bit with gigabit network, and then we discovered that the lightweight IP stack is not so cool when it comes to performance on a gigabit network. So there was the approach to go to the TCP/IP stack of Linux too. So the TCP/IP stack of Linux has the advantage that it focuses much on optimization. But the drawback of this is, of course, that it is pretty big and needs a lot of interfaces included. So you have a lot of porting work, a lot of maintenance work, but there's better performance. Yeah. So we have nowadays both of these stacks available on Genode as libraries, and you can choose if you want to have a slim stack or if you want to have a stack that is good in high performance. Okay. This is a rather old picture of how it works with the stacks. You have here the NIC sessions, and on top of that you set this lightweight IP plugin or the lightweight IP lib, and then you can have, of course, here the libc on top of this, and then your application. Okay. Now to the VFS approach. I I want to go a little bit into the history of VFS as it is without mistakes, because just to understand why we did things, how we do it. The first thing here is VFS is of course tightly one of the main features of Unix way that everything is a file. You can put everything into a virtual file system and then provide it as files on top. And at the other side, we have this Genode world, where we don't want to have such thing like a global namespace and all the rights that come with it, all the privileges. We want to tailor the privileges of each component according to the requirements. And to get the best of both worlds together, we have something like the Nukes runtime, one of its main features is the VFS implementation. We implemented the VFS in this, and it plays like its role is a little bit like the glue code between all the sessions that we have in Genode and the file API for the Unix programs or for POSIX applications. So at some point we discovered that it would be nice to have this VFS extracted from Nukes to use it also in other applications, to have a nice generic interface to talk to, regardless of which session you want, which resource you want to speak to in Genode. So we had this VFS lib, and we created the libc backend to accompany the VFS lib. And then we could have in each application a specially tailored VFS instance. Yeah? So what you can do with this is you have, like Norm showed it in the demo in the other presentation, that you have the root tree or the root VFS somewhere in this basic setup, and then you can give parts of this to other applications, and they only see these parts of the VFS in their environment, and can call it with the libc front end. Yeah. This is what we do when we go to these shades. Yeah. Okay. Then there was the need also to do this centrally. So you could provide one VFS to multiple applications at the same time. And you can see how this works here. We have one server component that has the VFS library linked to it, and then we have multiple plugins connected to it at the back end. The log plugin at this point, for example, enables you to write to the log, like it is done this right side, and the ROM plugin, for example, you can access images of Genode, so you can put it in as ROM modules and then CSS files. And all this goes to the front end is always the same. It's the file session, the file system session of Genode. So it's obvious. was a new question at this point. Some years ago, we wanted to use the stacks that we had with the libc plugins. We wanted to use such stacks with multiple applications at one time. So you have one stack only, and you have multiple applications that access it. For instance, when you have not so much IP addresses or something like that, or you don't want to redo all the IP configs as DHCP or something like that, then how would we do this? And of course, the simple approach would be at this point to introduce a new Genode session, a socket API session, and implement a dedicated multiplexer component. But this would be pretty specialized and not so reusable, so we thought about an inspiration from the Plan 9, the Plan 9 system. And this was, why don't we integrate this whole stack into the BFS server? And so the functionality of these stacks would be provided over files to multiple clients. So the clients would have to speak only with the file session interface, and at the back end it would be translated to network packets. Okay, this is the concept. Of course, we have something like the Linux IP plugin for the BFS library, and then you have your BFS server again and the file system session at the top of it that speaks with the applications. And yeah, how to get this? This like you have the LXIP plugin for the BFS creates a directory structure where you have this socket directory, and in there you have this information provided through files that comes from your DHCP. So you can read out your gateway, your netmask, your address, and so on. And you can also create new sockets by going into this TCP directory, for example, and write your read from new socket. And what you get there is then the name of the socket. And when you do this, the LXIP plugin creates a new directory with the name of the socket. And then in this directory you have new files that are in principle the control commands that you normally need to interact with the LXIP stack. And you can write, for example, to bind or connect with the informations that you want to provide, like the IP address or so you want to connect to. And then the LXIP stack would do, the LXIP plugin would translate this to reconnect in the LXIP stack. Okay. And then when you have accomplished the connection, of course, you can interact with local and remote and send data or receive data. Okay. And of course, on top of this, you can have then a file session plugin for the libc. And so you can talk, you can use in this case, unmodified applications that talk with the libc, that are built upon the libc for networking. Okay. A short overview of applications that run on top of this. So we have seen already a virtual box that runs on top of it. It runs directly on the NIC session to create a virtual device for its guest. And we have our components like DOSBox for games grade 3 or something like that, or the Edge server like TPD that run that read with the socket API from libc, and then we have this concept that this is routed through the FS plugin, the file system session to the FOSDEM server, and so on. Okay. And of course, we have the Skype scenario that was already presented today, where we have this runtime in it, where I can start an arbitrary runtime that I want to use for my daily work. And in this runtime I can have, for example, a Ubuntu VirtualBox, a Ubuntu guest in a VirtualBox, or TinyCore in a VirtualBox, to connect directly to a NIC session of the NIC router. Or then I initially wanted to present here two HTTP servers that I can talk to only over the TinyCore. So I can do a connection only in the TinyCore to these two through the DFS server. But unfortunately, I had some problems with HTTP servers, so yeah, this doesn't work that well. But in general, you see here, this was this NIC router. I showed the configuration some time ago, and you can have now, like here, this one VirtualBox that goes over the NIC router, connect to some websites, while we have the other VirtualBox with my Ubuntu, for example, and here I can also connect to websites, so it's multiplexed over the NIC router, actually, in this scenario that I use. Okay. So, that's for my part. Are there any questions? Yes.
I'm wondering about performance. And you said the Linux stack is more common. Is there a common reason for this, or maybe you can just tune and which is bigger factors, bigger.
Yeah. Okay. The question was, is there a reason to what I said that the LXRP stack performs better? As far as I understand it, the way that the LXRP stack has more possibilities or opportunities, more possibilities to tune the performance, to adapt to the device you have. So when you come into gigabit networking, close the door, this gets more out of the device. Excuse me, could you please wait a little bit? We have the call in progress. Yeah. Because the question is, we could also add this to the Elbit stack, of course, but we do fine with this solution so far. We have these two stacks you can decide, and the other side is, of course, if you would add these activities to the Elbit stack, it would get bigger and more complicated eventually. I don't know. We haven't took this approach. We ported the LXRP stack to get this performance to.
So I guess arguably people review that performance at some point.
Yeah.
So they will have to implement.
Yeah. But we didn't do it this way. I don't know. Maybe some of the other guys that are more familiar.
One thing is certainly the performance, because I'm not entirely sure, but I think the LWIP stack doesn't implement the receive window scaling. Just there's just a patch for the send window, or the other way around, basically, so that it doesn't adapt the window sizes dynamically in one direction, which limits the performance. But in case of LWIP versus LXIP, LXIP features more socket options, so you can well, there were some use cases where we needed some functionality that wasn't implemented in LWIP, and that's one of the other reasons why we choose to port a stack that is more sophisticated with its features.
And I would also add that LWIP seems to have less latency than Linux, the LXIP. But of course, if the throughput isn't as good, so there's sort of trade-offs of different characteristics.
Yeah, so the first thing is it isn't implemented simply in the so we didn't took the approach to implement it, to implement all features. I think it's what you said, Joseph. We just didn't do the implementation of further features into the LWIP stack. But instead,
the issue is we are not physically IP experts in the first place. And doing a IP stack, we need to know a lot of things and have a lot of experience in the test, but don't have the resource and the time to do it. And that's why we choose, because we've got a request that all the SOC ops supported we don't have, as WIP doesn't have. We choose to go this way and have two stacks. So if some customer, some client comes and wants, we can choose which stack. So there's no preference for us.
So maybe it ends up in the point that we are not so much the experts in this. The resources and the time.
Yeah.
I just wanted to repeat it for the micro.
Are you able to pass data with no copy between the different players?
Okay. So the question is, are we able to pass data through these different layers without a copy? And the answer is no. For mere security reasons. If you are, imagine you are in the NIC router and you have these different packet streams that are going on in different domains. You don't want to trust the guys that use these shared memory. And essentially, it's shared memory between the client and me. And if I'm in an untrusted domain and would say, okay, I take this shared memory and forward it to the other domain that is trusted in some way, it would be unsafe because I can take away the shared memory from the first one in a good way. So, yeah, it comes with this principle of security that you can't do it without a copy. Okay. I hope this answers it. Okay.
I wonder when I got that right. That's the first thing. In the NIC bridge, you virtualize on a layer 3. Yes. Why you choose that instead of layer 2 virtualization when you call it a bridge, and then also have the router to do layer 3 stuff?
The question here is why do we call it a NIC bridge? Why it is virtualizing on layer 3? I don't know if this answers the question, but I'm referring here to the OSI layer 3, so it's in IP.
Yeah, that's the reason is why you have two ways to virtualize on an IP level.
I don't know the name at this point. Is maybe a little bit misleading. I don't know. It's essentially a switch, and the functionality is the out proxy protocol in general. So don't let yourself be misled by the name that much.
Yeah, time.
Yeah,
So if you have
maybe after the.
Thank you.